Okay, on to part 2, and always you can skip ahead to questions, but 2.2 is particularly relevant to the rest of the courses. So I strongly suggest people focus well on understanding all of 2, really. So we're going to continue with the questions. So again, it's asking us to fill out this chart based on this formula. Oh, it's the same one from part A. So I need to get the formula from part A, which was 5x squared minus 7. Okay, I'll just keep that from the... So it's 5x squared minus 7 is equal to f of x. So on this next part, I can just let the computer do it, and I might bring back the other parts. So as you can see, compared to the first part, they went on the left side. First they did what's called a mid interval, where the thing we're interested in is right in the middle. Oh no, this is all to the left side. Left side by 1, left side by 0.5, left side by 0.1, left side by 0.01. Now they're going from the right side. And if you remember on the left side, we got close to, I believe it was 20. Yeah, I think it was 20 as we got closer and closer. Now we're approaching from the right side to see if we are approaching 20. And this is very important because later on, limits is how we do things. To see when we can't calculate the rate of change for something, we often approach from the left side and then approach from the right side and draw a conclusion. Because if you approach the same number from the right and left side, chances are that's the actual instantaneous rate of change. But in this case, they're looking at several average rates of change as you get closer and closer to 2. Okay, so let's do this one, and we're again going to we're just going to let this nice calculation that I did here do the work for us. So right here I've done the formula. Then I'm finding f of 2, which is 13. And then over and over again, so here we're starting with 3, right? We're doing 3. So I'm going to move on to f of 3 as the next thing. And then here I'm taking the delta x. So that's 3 minus 2, which is what we're looking at. We're looking at x is 3 and x is 2. And then here I'm taking my delta y. I'm making y3 the same as delta y, and I'm doing f3 minus f2. So that way it does it for us. And then I'm filling in my results. So obviously delta x is just 1, and delta y is 3. So we would put in our, see they've already done it here, 25 and 1. And what's the average rate of change? What's our delta y over delta x? And delta f of x is the same as delta y. Well, it's 25 over 1. 25 over 1, which is, of course, 25. So that one gave us 25. What about this next one? This next one you see here, they've calculated the delta y already and the delta x, and they get 11.25 divided by 0.5, which is equal to 22.5. So we're going down from 25 to 22.5. Then the next one they want us to do, so they're doing from 2 to 2.1 right here. So really I should have started with that one, 2 to 2.1. So f of 2, f of 2.1, so that's our y's, 13 and 15.05. Our delta x is 2.1 minus 2. I'm just going to have to ignore that sound, which is 0.1. Our delta y's is f of 2.1 minus f of 2, which is 2.05. And then it gives us our m for us. It takes our delta y and our delta x for us. So we would fill out of this table our delta x, we found it as 0.1. It was 2.1 minus 2, which is 0.1. Sorry, that's our delta x, so I'm going to put that over here. And our delta y we discovered, which was f of 2.1 was 1505, and the f of 2 was 13. So we'd write 15.05, was it? Yeah, minus 13, which is, of course, I'll just save some time, 1.95. And then over here, we did the division. 1.95 divided by 0.01 is 19.5, which I think is not what we go at, 20.5. So I got one of them wrong. Oh yeah, I got the 1505 minus 13 is not 1.95, it's 2.05. Which means 2.05 divided by 0.1 is 20.5. Okay, and then finally they're asking us to get even closer with 0.001 here. So again, I can let the, there's my f of 2 is always 13, and now this one is, we're looking at f 2.01, and it's 13.2. My delta is now my delta x is 2.01 minus 2, which is 0.01. So my delta x is 0.01. Notice it's 1/10 of the last one. And our delta y is going to be f 2.01. Oh, we've got a, yeah, which it's done. Minus f of 2, which is 0.205. So that means our delta y is 0.205. Notice it's more accurate and 1 decimal less than the previous delta y, which means 0.205 divided by 0.01 is the same as 20.05. What number does it look like we're approaching? And remember, the other one we were approaching was 20. From the right side, it was like 19.99 or 9.95 or something. Well, it's clearly from the left side, we're getting closer to 20. And the right side, we're getting closer to 20. So I can say, based on the trend of the average rates of change, I estimate the instant rate of change when x is 2, 20. The instantaneous rate of change, the instantaneous rate of change is probably 20 units of y per unit of x. So that's how you determine it. You slowly look at each thing one at a time. Here they're just giving you the data, which personally I find more difficult. They're giving you the data and asking you to analyze the data. Now you can put the data into Desmos, but it's hard to do. So they say analyze the instant rate of change, the height of the ball exactly 2 using the preceding and following interval method. So that means I would take delta x here and the delta y and divide them. And actually I would do it bigger first. I do that one first, and that one next. And then I'd go on the other side with the equivalent distance. So that was 1.5 on this side, so I'd go this one next, then this one next, and then this one next, and then I draw my conclusions. Then they ask us to do it using the centered interval method, which means I'm going to do this, and I'm going to take these on either side to see what their average looks like. But let's use the this method. So I'm going to take all of these. So the biggest one I'm going to do at 2.5, y is 32.38. So I'm going to take 2.5 and 1. That's their delta y's. Oh, sorry, 2. Sorry, it's 30.9 we're interested in. That's the delta y when x is 2 every time. So I'm interested in that, and it's 2. The delta x is 2 minus 0.5. Actually, let's just use the 1. Let's just use 1 instead. Okay? And then I'm going to take the next one closest to it, which is 30.9 minus 26.98. And the delta x I'm going to look at is 2 minus 1.5. If you want to get really accurate, you would add another delta y in there just to see where the trend is going. So you would do this one as well, 30.9 minus 17.78, and the delta x of 2 minus 0.5, which is equal to 1.5. This one's equal to 1, and this one's equal to 0.5. So you can see we're getting closer and closer to it. So you would take your calculator and you'd come up with, okay, 3.12 divided by 1.5, which is equal to I should use my keyboard for that. 2.08. So it looks like we're approaching 2 as a guess. This one here, 30.9 minus 20.6 is 3.3 divided by 1. Oh, that one's way off. So I'm going to make sure I got this one right. 3.9 minus 3 is indeed 3.12, but make sure I got the right numbers right. Oh, I got the numbers wrong. It's 11.78, which means the difference is not 3.2. It is 19, quite significantly different. And it's not going to be 1.5. It's going to be way off from that. 3.9, 20.6, and again, this is not 3.3. I must be drinking. It's 10.3, which means I'm 10.3 here. So that makes more sense. So 19 point, and you can make errors like this very easily. That's where data is a little bit more dangerous than formulas. So you can take a whole bunch of points with the formulas. 12.74. So you can see it's nowhere really giving any indication. And then this one, the difference here is a little less than 3. It's 3.92. And the delta x is 0.5, so 3.92 divided by 0.5 is equal to almost 8. It's equal to 7.84, something like that. Let's make sure we got all that right. So it's 30.9 minus 26.98 equals, none of that entered. Great. 30.9 minus 26.98. Enter. So I get, and that's wrong. So try to once again. Minus 26.98. Enter. 3.92 divided by 0.5. 7.84. So I got that right. So you can see I'm going from 12 to 10 to 7. So it's jumping quite a bit. You definitely want to have more points. But now let's take it from the right side. So now I'm going to take it from 30.9 minus, and I'm going to go all the way over to the 4. No, I'm going to go all the way to the 3.5, which is the equivalent distance. So that would be 2 minus 3.5. And then I'm going to take the next one over, 30.9 minus 31.4, which is the delta x is 2 minus 3. And the last one is 30.9 minus 32.38 over 2 minus 2.5, which is the same as minus 1.5 minus 1. Don't worry about the minuses. As long as you do it correctly in both of them, it'll be fine. And this one here, oh, it looks like looks like a sort of a parabola. And I should have analyzed the data and looked at it carefully, because you're going to see where this isn't going to give you a good answer. So 28, 2.9, 2.92. The rate of change is 2.92 divided by negative 1.5, which is, so it's going down now. negative 1.94. And then this one is the same as, this one is a negative, and here's, I'll show you what's going on in a second. So you get 30.9, 31.4, and this is where Desmos would have visually helped, actually. So you get 0.5 negative. And so the delta, the rate of change, is negative 0.05 divided by negative 1, which is 0.5. And you can see why we're not approaching something, because we're most likely looking at a parabola is equal to negative 1.48, and the rate of change is negative 1.48 divided by negative 0.5, which is positive 3.96, 2.96. Okay, so what's going on? Well, let's go back and look at our data, which is what we should have done in the first case. Time and height, and it's a soccer ball kicked in the air. So it's going up, 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 peak, down, 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 down. Now, all things with gravity, they go up fast at first, and gravity takes hold, slows them down, they reach their peak, they start coming down, gravity accelerates it. So all gravity will keep getting faster and faster as time goes by. And by the way, when did it hit the ground? After 5 seconds somewhere, because it's really accelerating here. So it's in the air just over 5 seconds. And it's the rate of change at 2 seconds. So here we can see the rate of change is just reaching peak, so it won't be that fast. And if we look at our going up rate of change as we get really close to 2, the rate of change is 7.84. The reason this one is slower is because, and these are also off, is because as the peak right here is going to be the slowest. This is on the left side. So since this is the peak right here, and I'll mark it here, the second 2 that we're looking for is over on this side, which means as I approach the 2 from the left side, and the beginning here from the left side is probably more accurate rate of change. But as I go on to this other side, the rate of change I'm measuring is like this. It's not giving an accurate look at what's going on at all. If anything, the only accurate rate of change is going to be happened from the left of the peak of the soccer ball, because the other side is negating all my averages here. So really, I should be looking at this one and this one. On this side, the reason it's still positive 0.5 is because it's sort of still going up as a slope from this 2 second point. The line is still sort of going up, but it's not an accurate portrayal of what's going on at all. If anything, putting data into the system will give you an accurate thing. Now, this is a good example of how the average centric system will give us a better idea of what's going on, because I'm going to get a slope like this over and over again, except the very beginning. So when you look at this one, you can't really draw conclusions. It looks like it's going down to 7, then all of a sudden you get these minuses and small numbers going in. And that's when you have to analyze what's going on with the soccer ball. But let's look at the average method. The average method says, I have to take the average here between these 2 points, and then the average here between these 2 points, and maybe even the average here between these 2 points to see what's going on. So let's do that instead of what we just did. So between these 2 points, the delta x is 1, and the delta y is 32.38 minus 26.98, which are the points on either side of it. And the delta x is 1. 2.5 minus 1.5. The next point and I'm just going to do the next points first instead. The delta y is 31.4 minus 20.6, and the delta x is 3 minus 1, which is 2. And the last point is 27.98. And it doesn't matter which ones you minus first, so long as you keep the minus in the same order. 11.78. And the delta x is 3.5 minus 0.5, which is 3. Okay, so let's come up with our delta y's here. 32.38 minus 26. Sorry, my brain's slow right now. Equals 5.4, and divided by 1 is 5.4. So right there, we get 5.4. So my rate of change here, my ROC here, is 5.4. Let's do the next one. The next one is 31.4 minus 20.6, 10.8. What was our delta x? It was 2. So that's 5.4. And our next one is going to be 27.98 minus 11.78 divided by 3, which is 5.4. So this is a great example. What's this teaching us? It's teaching us that we have to understand the data before we analyze it. And if I look at this, so height is 0.5, so that's the height of the soccer ball player, 0.5. The vertex is right there at 2.5. So that means if I write it in vertex format, I can do it something like this. X minus 2.5 and plus 32.8, 38, and then I just need to figure out this at the end, and I could do that with by plugging in a couple points. And that's the nice thing if that is indeed the vertex. But let's see if I can get a rough idea using this. Probably should have kept that tool around because it's pretty useful. But anyway, so y is equal to x minus 2.5 squared plus 32.78, was it? $32.38. And let's go with negative. And we're just going to restrict our x is bigger or equal to 0. And we're trying to get that at about just after 5, and we're trying to get the intercept. So we need a slight stretch, yeah. A slight stretch. Almost. Try 5. Too much. Oh no. Yeah, a little bit more. 5.2, something like that. 5.1. Close. Yeah, that's close enough. That's close enough. And we can see right there is the point we're looking for. Now, why did the average work better? I'll show you why. And I think I already explained it. Because if you look at this here, and I'll just expand it like that because it's easy. And if we're studying this point here, which we are, and we take the slope around it, the average slope around it. Okay, I'll take that one. And then I take this one. And then I take this one. and I keep doing the same amount behind it, you can see that those average slopes work a bit better at coming up with the actual rate of change, which is like that. Whereas if I take the interval left and right, I'm getting slopes on the left that look like this, which are somewhat accurate, but I'm getting slopes on the right side that look way off and don't give me any information at all. So you really have to know what you're studying and realize to get a good idea of this slope here, you really have to focus on this side of the parabola. And the reason the average works is because the slope is pretty much preserved on either side. And let's find out, I'd like to actually see what the actual f prime of 2 is. It's 5.1. Does that make sense? Yeah. So we're coming up with 5.4. The best way to come up with this would be to have this formula and take 1.99 and take 2.01, or it's just 2. And take the delta x and delta y of that. So m is equal to f of 2 minus f of 1.999 and divided by its difference. Put a bracket here and a bracket here, and its difference between 2 and 1.999. And there you get a much better idea of this. That's where formulas give you a much more accurate than raw data. Because if you look at it, we're only working with like 9 pieces of data, 10 pieces of data, 11 I think. It's not very good. Which estimated do you prefer? The average one in this case. Okay. Population of raccoons, and sorry for if I go on and on and on, but I think understanding these things is better. So I would strongly suggest always figure out your graph before you proceed. So population can be modeled by this. It's in the wrong order. What is it? What kind of graph is this? What's the correct order? Well, the population based on time, where time is months and p is number of raccoons, is actually 4t squared plus 30t plus 100. So what kind of graph is this? It's a parabola. Is it facing up or down? It's facing up. Where's its y-intercept? Its y-intercept is at 100. So that means at time 0, we're starting with how many raccoons? 100. What do you think it's going to do? It's probably going to go up and then descend. It's only interested in 2.5 months. So that means after 2.5 months, you'd punch in 2.5 into t. Determine the average rate of change between 0 months and 2.5. Estimate the rate of change of the raccoons in the population exactly 2.5. Explain your answers for A, B, and C. Why are they all different? Okay, let's figure out something about this. First of all, let's factor out, before we ever proceed, let's factor out the 4. So you're going to get t squared plus, yeah, it doesn't work out perfectly, but it's okay, 7.5t plus 25. Okay, that's interesting. If I were to come up with a factor of this last one, I'd have to come up with something that multiplies out to 25 and adds up to 7.5, which is going to be hard. But I'm going to complete the square instead. T minus 3.75, and that means I'm going to be creating a 3.575 I don't want, all in brackets, plus 25. What is 4 times 3.75? Or actually, it's not negative 3.75. I'm going to create a 14.0625 that I don't want. And if you don't know what I'm doing, go practice your completing the square. It's very important. Okay, and then when I multiply that by 4, I get negative 56. And when I add that, well, that's not going to, does that mean this population is declining? So let me make sure. I believe it's declining. Okay. So that means I'm left with 4t minus 3.75 squared minus 3.75 times itself times 4 times negative 4, really. Plus, oh no, plus positive times positive 4. Yeah. Plus 25. Negative 30. So when I complete the square, I discover this, that this is the factored formula. Let's get rid of all this. And then don't forget that there's a square right here. So when I do this, I realize, oh, wait a minute, my at 3.5, 3.25, the population is going to be negative 35, 3.525. So that means it's going up here and it's crossing here at the 100. So that means this population of raccoons is declining. Let's make sure that's true with Desmos. Oh yeah, and it's facing upwards. Sorry, yeah. So I got that wrong. It can't be declining if it's facing upwards. That could have been this side of it. Okay, so how did I get that wrong? So when I complete the square, I get this. 4t squared. Oh, I know what I did wrong. It's plus 100 over there. I wasn't supposed to touch the 100. Not plus 25. So if I complete the square, this is what I'm left with. Right? Where I'm just taking the 30 out of this. And then when I complete the square, it's actually negative 56. What did I come up with? 3.75 times 4 negative times itself. Yeah, 3.75 times itself. Times 4, and it's negative. And then when I add 100, that's the problem, is I shouldn't have converted that. 43.75. So this is the correct factoring. And I got to do f of t. There we go. Now it still didn't get it right. Oh, I know why. Because now it's no longer this. And it's no longer this. There's no t there. And this is to the power 2. And I still got it wrong. Oh, because I've left this in there. There we go. So now we've got the correct factored. And we're only caring about when t is bigger or equal. Actually, we're caring about 0 smaller or equal to t, smaller or equal to 2.5. And we're taking that same restriction for this one. Now you might think this is cheating, but it's not. It's helping you understand what's going on. And I just completed the square wrong. Now, determine the population of raccoons at 2.5 months. So that's f. What's f of 2.5? The population is 200, give or take. What's the next question? Determine the average rate of change between 0 and 2.5. Well, we know at f is 0, it's 100, right? And we know f at 2.5, it's 200. Therefore, the rate of change is going to be 200 minus 100, all divided by 2.5. So over this entire 2 months that we're interested in, 2.5 months, the rate of change is 40 raccoons are being born a month. estimate the rate of change of the raccoon population at exactly 2.5. Okay. The rate of change, which we'll call M2, is going to be F of 2.5 plus 1.0001, that's my H, minus F of 2.5 divided by 0.00001. That's my H. And why is it giving it undefined? Get rid of that. Still undefined. Because there's nothing. I had to do minus, sorry, because there's nothing on the right side. There we go. And I've got, why is it negative though? Let's just do 2.49999. Oh, and I've got to do the other way. It's got to be 2.5 minus 2.49999. And then this has to be matching if you just do it like this instead of the way I'm screwing it up. There we go. So the rate of change is 50 there. And the reason, explain the difference, is when we take a very precise point near the rate of change over an average, you're going to get a discrepancy. And that's because also, since the average ended at this point we're studying, it's really putting in all those raccoons that weren't even born yet. It's actually not showing the correct rate of change. You can probably see it better when there's no restrictions on it. But you can see it just turned around here, and when it reached 100, it was just starting to climb. So the average rate of change is going to put in all these numbers down here that pull the average downwards and make the rate of change seem steeper than it is, or seem less steep than it is. So visually, if I'm going to write this visually, if I'm doing a really fat parabola, you can see it better. You can see here that we've already covered that the rate of change here is much steeper, like that, than if I take a average rate of change, which is what we just did, from here, and I'll make this green line, here. Look at their slopes. Isn't it obvious the rate of change in the green line is not as accurate as the instant radius change of the red line? And that's because this bottom slope that I'm pointing at is sloped slower than the red line. When we take the average rate of change, we're essentially taking the rate of change of this red line and we're averaging it with the instantaneous rate of change at this green line. And we're coming up with this new average rate of change, which is the blue line. So the reason we're not getting something close to the actual red line that we're interested in is because we're factoring in this very slow slope down here that comes up with this blue line, which is the 49.9 we came up with. So you'll never get an accurate look until you get really close to instant rates of change. They're different because the average rate of change is factoring in the very low numbers that the raccoon population was showing in the beginning. I hope that's clear. Practice. Estimate. Okay. So 6x squared minus 4. So I'm definitely going to use a Desmos for this. 6x squared minus 4. First of all, let's get rid of all this. And there we go. We're looking at a parabola that starts way down here at -4. Okay, and it has x-intercepts there and there. All right. Now let's also make it f of x and stick with f of x instead of y. Okay, what's one they're interested in? When x is -2. X is 0 and x is 4 and x is 8. Let's look at these points too first. Okay. 0, 4. They want 4 for this one. All right. So there's that one. 0, comma, f of 0. There's that one. There's that one. And then that other one's way off the charts. Which ones do you think are going to have rates of change? What's the rate of change of this one here? It's going downwards, right? It's going to be big, negative, and sharp. What's the rate of change going to be at this one? It's going to be a flat line. It's going to be 0. What's the rate of change going to be like this one? Probably twice as high, but positive as this one. And then this one up here is probably going to be close to twice as fast as the f of 4 one. Wouldn't even say twice. It would be twice squared, so it would be 4 times as fast. And then times 6. Well, they're both times 6. So I'll say it's 4 times more steep. So I'll say the 8 is going to be 4 times more steep than the 4. The 4 is going to be 4 more steep than the 2, but also opposite signs, and this one's going to be 0. So we're going to start with the f minus 2. Do that. And what I'm going to do is figure out the slope, or the instantaneous change. So what's a good point to take near it? So I'm going to take f of minus 2, which is 20. So let's just take 20. And I'm going to subtract f of minus 2.001. Okay, and then I'm going to divide it by the difference of between f of 2. I should have translated it to 20. I should have just left it as f of 2. What's the difference between them? What's the h? 0, 0, 1. So we can see it's negative 24. So I'm going to guess that the 4 one is going to be 4 times that. So 48, 96, and positive. Why is it 4, not 2 times that? Because of the squaring feature. Okay, now let's figure out the 0 one. This is going to be interesting. So now I'm going to do m2 is equal to f of 0 minus f of, let's say, 0.001. And of course, I'm going to divide it by 0, 0, 0, 1. Look at that. What numbers? I know it's negative, but what number does it look like it's approaching as I add more zeros to this? Looks like it's approaching 0, especially if I took it on the other side of it, right? Instead of 0.1, I did 0.999, and then did this. Oh, 0, 0, negatives. Yeah, this is on the other side of it. It's approaching 0. Either side, one's positive, one's negative. I actually had to do this because I actually did it improperly the first time. It's approaching 0, so that's flat. Let's take the next one. I'm going to add a expression, put it down. And we're going to take an m of the difference, m3 is going to be f of 4 plus 0.001, so that's our h, minus f of 4 divided by, I had to put a bracket over here, divided by the h I added. So there you go. Look, it's 48. Oh, it's twice as much, not 4 times as much. Okay. Well, I stand corrected. It's twice as much and positive as the other one, which I'm going to therefore guess that the 8 is going to be twice as much as the 4 and positive as well. So finally, the last one, we're going to do m4 is equal to f of 8 plus 0.01 minus, and I forgot to put a bracket again, which keeps screwing me up, minus f of 8. So I took a point just after it, divided by my h. 96. So yeah, twice as rapid as the 40 as the one at 4. So you can see that the rates of change were indeed doubling based on, and one was negative based on where they are. So understanding the graph really helps there. An object is sent through the air. Its height is modeled by this. So it's a downward-facing parabola. If the height of the object in meters and the x is the time in an object, estimate the instantaneous rate of change of the object at the height of 3. Okay, I'm going to start just doing the specific question at hand. Okay, this is the one. Sorry if the other ones were confusing. Okay, let's try to understand first a few things. What's the y-intercept of this? Is it downward facing? Yes, it's downward facing. It's got a negative. What's the y-intercept? So it's going to go through a point either here or here. That's 0, 65. I don't know yet. Let me factor out the minus 5 in front. So I get minus 5 x squared plus, minus 3 over 5 x. Does that make sense? Yeah. And I'm only going to factor out the minus 5 in the first two terms. So the plus 65 is still there. And keep in mind the squared is still there. How did I get the minus 3 over 5? Well, when I factored out 5 from this term and this term, I had to divide them both by minus 5. This one canceled out. And this one became negative 3 over 5. And the 5 there, negative 5 therefore went in the front. Which instantaneously tells me that the if I were to partially complete this, I would get a minus 5 x minus, what's half of 3/5? That's how you do this, by the way. Half of 3/5. It's the same as multiplying by half. It's 3/10. So that instantly tells me the x factor of the vertex of this squared, and I don't know what the plus is yet, but that instantly tells me the x factor of the vertex of this is plus 3/10, which is just on the right side of the axis, which means this peak here, when it crosses 65, is very close to the vertex. The vertex is just going to be on the right side of that, and it's going to be essentially measuring everything after that. If I wanted to continue and complete the square, I could, but it's more important to understand where the vertex is. It's just close to that 65, which means at 3 seconds, this puppy's accelerating downwards. Let's get our y value for that. What happens when at 3 seconds? When I plug in 3 seconds for this, my h of 3 I'm going to find a better one for that, probably that. Let's see, is that better? No, that's horrible. Might be this. No. I just did that. Doesn't matter. So my h of 3 is equal to minus 5 times 3 squared. What's 3 squared? 9. What's minus 5 times 9? Minus 45. Plus 3 times 3. What's 3 times 3? 9. Plus 65. What's negative 45 plus 65? Plus 20. So it's plus 20 plus 9. What's plus 20 plus 9? 29. So therefore, at the peak, or at 3 seconds, it's at the coordinates 3, 29, and we also know it started at roughly height of 65. So it's descending quite a bit. It's descended 36 meters in 3 seconds. So if you can quickly get an idea, it's descended 36 meters in 3 seconds, so it's falling at roughly a rate of 12 meters per second. Now, that's an average rate of change, because I essentially just did average rate of change from its max height. Let's now look at an instantaneous rate of change, which means I need h of 3.001. And it also means my h, and don't confuse that with what we're working with, is 0.001. So for this, I would need to do minus 5 times 3.001 squared plus 3 times 3.001 plus 65. And this is going to give me a time just to the right of the thing I'm interested in. And it should be negative. And ultimately, I should get a negative answer because I'm downward sloping. So if you don't get a negative answer, you put your h 3.1 on the wrong side of the other one. So then I'm going to take all this data, and I'm going to do h 3.001 minus my h3, all of it divided by my h, which is 0.001. So the question is, what does this come out to? So I'm going to do calculator method. So 3.001 squared times negative 5 is that. So we're going to select all, and we're going to copy it. So it's equal to that plus 9.003 plus 65. So all we have to do is add 65 and 9.03 to it. And we get this. Which is the y just to the right. So that means that at 3.001, the y value is exactly what I just copied and pasted. It's that. So now if I put it into this formula, I get 28.97295 minus, what was our height at h3? That. All of it divided by 0.001. So we're going to take this. We're going to minus 29, and we're going to divide it. Oh, before you do that, let's just do that so that we don't, we're going to hit equals. There we go. And then we're going to divide it by 0.001 because order of operations almost screwed me there. Negative 27.05. So that's my rate of change, which means my instantaneous rate of change at 3 is negative 27 meters per second. Is that close to the average rate of change I took above, where I said it was 36 divided by 3? No, it's not. And that's because we have huge acceleration. Always verify your work. So we're going to take minus 5x squared plus 3x plus 65. So there it is. We're going to also see where it's, if I was right about its, oh, I was slightly off. It's actually descending already at that point. We're going to find our f of 3. Oh, I did an error there as well. I had it as 29, so I did an error. Let's see where I did it wrong. Let's make sure I did it wrong, actually. Yeah. So where did I do it wrong? So 3 squared is 9, minus 45, plus 65 is plus 20. 3 times 3 is 9, 29. Well, I got it right in my calculations. Minus 5x squared plus 3x plus 65. Oh. There, so I was right. It does peak just after the y-intercept, and f of 3 is 29. Now I'm going to find my f of 3.001, which is just a second after. Then I'm going to take that. I'm going to find my slope, which is f of 3 minus my f of 3.001, all of it divided by my h that I used. And I put it in the wrong order. Why is it important to have the 3 after? Because, and maybe this is a great point to go through, because my delta x and my delta y have to match. So my x at this is 3.01 and my x here is 3. So I can reverse it up here if I want, but if I do that, I also have to make sure that my x's, my delta x's, match the corresponding y's that they're associated with. Otherwise, what will happen is your slope symbol will go from negative to positive or from positive to negative and give you an incorrect error. So in this case, you can see this x value is on the wrong side. It's associated with the 3 when it should be associated with the 3.01. So when you do it quick and dirty the way I'm doing it, you will make errors. So I caution you to always make sure you have all your steps in there and make sure your x values. So I should have always had this as 3.01 and this is 3 if I was just going to use an h of 0.1. Okay? And that gets easier to see if you put the correct x's in that's associated with it, because that's the same as 0.001. And there we get the slope of negative 27.005. And I think I got negative 27 and rounded up. So we got it correctly. A family purchased a home for 125. Appreciation, which means it went up in values, based on a growth curve. This is a growth curve, where h of t is the value of the home and t is the number of years the family uses. Estimate the instant rate of change at the start of the 8th year. The start of the 8th year. Okay. So let's first of all understand this formula. It's a growth curve, correct? What do growth curves look like? Well, they're always above the y value, unless they have a vertical increase or decrease. There's no vertical increase here. So this one starts here. What is its base? Its base is 1.06. So that means at 0, when t is 0, y is going to be 1.06. So that means y to the 0 will become 1. 1 times 125,000. 125,000. So the 0, it'll be 0, comma 125,000. What will it be when t is 1? When t is 1, 1.06 to the power of 1 times 125,000. It'll be 132, 500. And now each year, this house is going to go up 6% in value. And sure enough, if I wanted to, I could just add 6% to that, 6% to that, 6% to that, and get to my next value. But all I really have to do is figure out what my h is at 8 and what my h is, which would be called home value. So the bummer is they keep using h. So I'm going to use f instead. So I'll value at the home at 8 years, and just figure out the value of the year either after it or before it. Okay? Let's use before it this time. So that's this time. What's my h? Okay, how do you figure that out? Well, just do it slow if you want. I'm going to take my value at 8 and subtract my value at 7.9999. And it's all going to be divided by 8 minus 7.9999. And if you take your calculator out, you're going to get 0.0001. That's my h. And sure enough, I could have done it as this. 8 minus h. And then it would be that. I could also put the plus h over here instead. And that would work as well. And maybe that's a good way to think of it. If you're putting it on the right side, it's going to be a minus h, and if you put it on the left side, it's going to be a plus h. Well, yeah, that makes sense. That way your h will always stay positive, whatever unit you're working with. Okay, let's put this in, 125, 1.06. Let's call it value based on time is equal to 125,000 times 1.06 to the power of t. And let's try that. And I forgot that. Does that work? No. What are you having trouble with? The v? Okay, let's do f. Oh, you're having trouble with the comma. Yeah. And if we put in a table of contents, we can even do 0, 1, 2, 3, 4, 5, 6, 7, 8. There's the value of the home at f of 8. But if we're going to do the rate of change, we're essentially finding f of 8. Plus h. Let's put it exactly like that. We're going to subtract f of 8. And we're going to divide it all by h. Now all we have to do is figure out our h. So now we click on h, and we're going to make h 0.0001. And we're going to get that. And how does that interpret it? That means the house is increasing in value $11,609 per year precisely at the 8th year. It's going to increase much more in the 9th year because the house is worth more, and it's going to increase less on the 7th year because the house is worth less. Let's look at that. Let's use a 7. Yeah, the house is only increasing 10,000. Let's look at year 2. Oh, the house is only increasing 8,000 a year. Let's look at year 8 again. Okay, the house is increasing 11,000 per year. Let's look at year 9 now. Oh, the house is increasing at 12,000. Let's look at year 10. The house is increasing at 13,000. Notice those numbers are getting much bigger, much faster because it's exponential growth curve. It's 12. 14,000. So that number means how much is the house increasing per year at that precise moment, though. That's all it means. Next year it could be increasing. It will be increasing more because it's a growth curve, but it only means how much is the house increasing in value at that precise moment of H0001. In other words, at a tiny, tiny interval in between 8th year and like 0.0001 of the year. And that would be the answer. Now I should start pulling up the answers to the back of the book to verify that this is to show you that this is the correct method. And I will next thing. So the population of town is increasing in thousands. What is the average rate of change? Does your answer part A make sense? So it all depends again. Let's understand this curve. Now I could factor it out and figure out the vertex, complete the square, but I'm not going to. Instead, I'm going to keep this wonderful formula here. And I'm going to keep this wonderful formula where we can set H, and I'm just going to change this to our new formula. So it's obviously a downward facing parabola. And you're going to understand a lot more when you see it. And it's negative. Plus 36t plus 6. We're going to get rid of that. This doesn't matter right now because we're not doing 12. We're going to look at it though. So this is a downward facing parabola that happens to peak at 12,222. So that means everything on the left of 12 will be a positive slope, and everything on the right of 12 will be a negative slope. Keep that in mind. So it's a population of a town, which means this town's population went up and then went down. And what would cause that? Well, gold mines. Gold mines in the gold rush in the 1800s caused that. People would rush to a town to mine the gold. And then as the gold ran out, they'd leave the town. Happened all the time. What is the average rate between 2000? So I guess 2000 marks 0. So that's 0 to 24, right? You got to remember that it's 0 counts as 2000, where t is the number of years after 2000. So that means 0 here is right there. If I zoom in a little bit better, 0 is right there, 0,6. So the town started with a population of 6,000. And then from 24, remember it peaked at 12. And then at 24, it doesn't look like it went up at all, does it? Over here, 24, it's also 6. So if I were to take the rate of change between this, I'd be drawing a straight line to here and here, and it would look like the town's population never changed in 24 years. That's where average rate of change is not useful for some data. So 0, and just to show you, f of 0, we're going to take the f of 24, and the f of 0. And what was the difference between those? 24. Look at that, rate of change 0. And I could draw a line in between that and show you, but I'm not going to. Let's look at the next question. Does your answer to part A make sense? Does it mean that there was no change in population? No, it doesn't. It means that it's on equal sides of the parabola. Explain your answer to part B by finding the average rate of change from 20 to 2012 and 2012 to 2024. Well, we know 12 shows the peak of the population. So it's going to show a negative decline from 12 to 24, and it's going to show a positive decline from 0 to 24. So from F12 minus F0 divided by 12, the rate of change is 18,000 people per year. And then from F24 minus F12, divided by 12, the rate of change was the opposite, negative 18,000 per year. So something brought the people there right up to 2012, and then afterwards they went away. For what value of t is the instantaneous range in the population? 0. At the vertex. That's the only place you can find an instant rate of change of 0, at the vertex, because that tangent line that we draw there will be a flat line. And to prove this, I'll show you what f of 12 plus h minus f of 12 divided by h is, and I'll put h at 0.01. 0.000001. Oh, we're not getting a good idea from that. There we go. 0. It's approaching 0. The more zeros I put in there, you might say that's not a 0 anymore. Yeah, it is. It's just, there we go. You can get a better idea. 0. There. You see that? As I put more zeros, it finally gives up and says 0. And that's the only spot. A peak of a vertex is the only spot where the vertex turns, the slope is going from positive, turning to negative, and it's 0 at the peak. The way you throw a baseball up in the air, and it hovers for just a moment at the very top of its path. She purchased a new car. It's depreciating. It's going down in value. So notice this is less than 1. That's the sign of a decay curve. Any value above 1 with an exponent of 2 is a growth curve. Any value below 1 with an exponent of x or t is a decay curve, where t is the value of car. What was the value of the car in year 0? Well, 0 to 0.93 exponent is 1 times 1899. So that was the initial value of the car. It even said it right there. Estimate the instantaneous rate of change. So how quickly is the car losing value when it's 5 years old? Well, understand again what decay curves are measuring. Decay curves go down like this, and right here is when it's going to have its max value, and after 5 years it won't be losing as much value as it is in the beginning. In the beginning it's losing the most value, and then it's kind of leveling off. So let's have a look at this curve. Get rid of the other ones. And the value of this car based on time is 18,999 times 0.96 to the power of t. So let's have a look at the formula again. 0.93. Okay, it's losing 7% of its value every year. Now I'm got to put the y-axis on something I can see here. So we're going to look from 20,000 down to 17,000 by steps of 1,000. And the x-axis, we're just going to look from 0 to 7 years, steps of 1 year. There we go. There it is. So there's its value in year 0. We can even slide it and see that by year 5 it's worth 13,000. So it's gone down by 6,000. But how fast is it losing its value? Well, for that we need to find the slope, the rate of change rather, at v 5 plus h minus v5, all divided by h. And for that we need to have an h. And by the way, I have to put in a big V so it knows what I'm talking about. Let's go back to f so it accepts it, and we'll put f there and f there. There we go. Now all I need to do is set my h at something very small. And we can see the car is losing roughly $960 per year. Minus means it's losing. depreciating. How much is it losing in the 4th year? 1,000. How much is it losing in the 1st year? 1,200. So it's losing much more in the first couple of years, and that's actually normal for curves. How much is it going to be losing in the 7th year? Only 829. So the answer to this question is what is the instantaneous rate of change of this car at year 5? It is negative $959.19 per year. Okay, next to a diver is on a platform. He's 10 meters up. And he jumps. So that means if we're looking at a graph, we would draw it like this. He is standing here. And this is not in the correct order. But that's his height at 10. So he's up here at 10. And he falls. Determine when the diver will enter the water. Well, that's when this is 0. When h is 2 is 0. And there's another one over here that doesn't exist because that's negative time. Estimate the rate of change the diver's height above the water is changing as the diver enters the water. So just as he enters the water, in other words, we've got to find this time to find the rate of change. How do we find the time? We set this to equal to 0. Zero is equal to 10, let's put it in the right order, minus 4.9 t squared. I'll use t squared like this, plus 2t plus 10, that's the right order. We can factor, but essentially we want to find two numbers, and we're probably going to have to use the quadratic equation for this. I suppose I could factor, but we're essentially going to have to find two numbers that multiply out to negative 49 and add up to plus 2. And as you can see, they're going to be fairly close together, and they're not going to be perfect. So this is where you'd have to use the quadratic equation. So I could use the quadratic equation, but I'm going to use a quadratic equation calculator. And I'm going to put in my a. So we look at this. My a is negative 4.9. My b is 2. And my c is 10. And then you click calculate. That's going to give you two answers. One, root x is minus 6.3. It can't exist. The other root is x is positive 1.64. So that's the one we want. So that means he hits the water at h of 1.64716. In other words, time is 1.647 seconds when his height is 0. So that means we have to calculate a rate of change. And yeah, I'll do it slow this time. I'm going to do his height based on time is equal to negative 4.9 t squared plus 2t plus 10. So here is that graph, and we only care about anything where x is bigger or equal to 0. Or t, rather. So there we go. He jumps, he kind of goes up a bit, and then he starts coming down. And sure enough, he hits the water at 1.647, which is what we have, 1.64716. Which means I have to calculate his h of 1.647. Did I just say it was? 1.64716. And there's his height, pretty much 0. 0.64 64716. Interesting that I didn't quite get 0, but good enough. I guess rounding error, but it doesn't matter. So that means to figure out his velocity as he hits the water, I'm going to just look slightly before him, and it's going to be negative because he's going downwards, right? So that means I'm going to take f of 1.64716, and what is it slightly before? It's minus h. What's my h going to be? 0.001. And I'm going to subtract, and I've got to put a bracket again. I always forget the bracket. And it's h of t. And I'm going to subtract h of 1.64716. And I'm going to divide that. When I subtract them, it's negative 0.001. And I can see that his speed is minus 14.14167 meters per second. If you want to do that the long way, you would just find your h of, let's see if I can do it. There we go. You would find hit your height at that point. In other words, what is my h at this? And then you would find your height at the 1.64716. So this is just a little bit before that. And then you would take your first one, 0.001367444636, and you would subtract the negative, or if you want, what's a better way of seeing it? Yeah, you would subtract it. So you would subtract the negative 0.00004672144, and you get that. Just call it delta y3 for delta 3. And then you take your y3 and you're dividing it by negative 0.0001. You get negative 14. Why is it negative? Because this last one, this one here, 1.64716, has 0.001 subtracted off of it, and then minus that. These are my delta x's. And you can quickly see that this one, when you remove the brackets, cancels out this one. Which leaves that. So there's my downwards rate of change. So just before he's hitting the water, he's going 14.14 meters per second. To make a snow person, snow is being rolled in the shape of a volume, and the volume is looking like that. Now that's a cubic, so cubic looks like this, but volume is only concerned with the right side of the cubic, where r is the radius. Use two different methods to estimate the instantaneous rate of change of the volume of the snowball when r is 5. So I'm going to approach it from the left, so I'm going to subtract an h, and I'm going to approach it from the right, so I'm going to add an h. And I'm going to use f of x minus f of x minus h, and then I'm going to use f of x plus h minus f of x. So it's 4/3 pi r cubed. That's the formula for a sphere, by the way. So volume based on radius is equal to 4/3 times pi times r to the power 3. There you go, that's volume. And we're looking for volume 5. So I'm going to add one where I have 0.0001, so that's just to the right of volume 5. And I'm going to have one that's just to the left of volume 5. And then I'm going to take my rate of change between, I'm going to call it M2, M1, is equal to my V 5.0001 minus my V5, and it's going to be divided by 0.001, and I'm going to a rate of change of 314 meters per meters cubed per meter. And then my M2, I'm going to do it slightly different. I'm going to find my V5, and I'm going to subtract just to the left of that, all divided by negative 0.0001. Oops, sorry, positive, yeah, because it's the same thing. It's 5 minus 4.999, it's 0.1001, and 5.001 minus 5 is 0.001. So this one is simply looking at the rate of change just before the 5, and this one's looking at the rate of change just after the 5. And they're both pretty close. You'll notice they're slightly off. This is 0.6 and this is 0.5, but you can see the rate of change is roughly in that neighborhood. So you could average those two. You could take average is going to be equal to M1 plus M2 in brackets divided by 2. So there you would take your average of those two, and you get a good idea of how much those that volume is changing based on each centimeter, sorry, not meter, centimeter. Hope you understood that. If not, feel free to ask me questions in the chat below, comment section below, or in person. Then he's going to drive to his grandparents. How can you determine his average speed for a part of his journey along the way? Be as specific as possible. Well, he would have to know his speed at 2 different times. So he'd have to look down at his speed at, say, 2 hours into his trip and then 4 hours into his trip, and that's a 2 hours difference. So you'd have to add those speeds together and divide. He could also measure the distance he is far away from his grandparents at one time, and then his distance at another time, and then his rate of change will be his speed. Because here's something you should realize. If I am looking at a trip and I'm measuring it based on distance over time, so distance is on the y-axis and time is over here, his rate of change is looking at delta y, which is his change in distance, over his delta x, which is change in time, which means I take delta y, delta distance, over delta time. And what is distance divided by time? Velocity, speed. So I'd have to look at his distance over time. So on this part of his trip, he'd figure out either how far he is from home or how far he is from grandpa, and mark down the time. And then on this part of the trip, he'd do the same. How far is he from home? And mark down the time. Then he would subtract his distances and subtract his times and do delta distance over delta time. And it depends which part of the trip he's interested in. That's when you would determine the time. Maybe he's doing city driving for the first half and country driving for the last half. So he would determine his delta D's and delta T's in the city, and then he'd do it again for the country to see if he's going much faster. This is a table. At 0, it's 400. Something's warming up. Something's warming up, and it looks like it's warming up faster and faster. 10, 25, 25. 10. Between that, 15 to there, 25 to there, 20 to there, 25 to there, and this last one, 35. Use the data to determine instant rate of change of the temperature of the oven at exactly 4 minutes. Use a graph calculator to determine the quadratic model. discuss why your answers for part A are different. Well, they're different because when you have seven sets of data, it's not going to give you as precise answers as the actual equation. So I can tell you right that. What's a better estimate? I mean, technically, when you come up with the equation, that's based on 7 points of data. It's not going to be that exact an equation, but it's going to give you exact answers. I mean, I personally think using the actual data is going to give you the best answer, but let's look at ways that you don't need a quadratic equation for this. Actually, you know what? Yeah, here's how you do it in Desmos. So in Desmos, you set up a table. I'm going to have to go soon, by the way, so I'm going to have to cut this short and resume the questions. So you just add a table, and you put in your time. So our time is going to be 0 through 6. 0, 1, 2, 3, 4, 5, 6. Our data is going to be 400, 390, 375. And it's going to plot it for us on the board. And 350, 330, 305. And what's our last one? 270. So I think this is going to be a decay curve, so we just need to see the y-axis further up from 270 to 400. There we go. What's that look like? It's either a parabola or a decay curve, isn't it? So let's look at first differences. I'm going to copy this and see if we can get a better idea of whether this is a decay curve or a parabola. What's my first difference here? 10. So I'm going to set up a little box like this, and I'm just going to do the differences in blue. First difference is in blue. Down 10, so negative 10. Negative 15. Negative 25 between this one and this one. Negative 20. Kind of did a weird thing there. Negative 25, back on track. Negative 35. Let's see if I got that right. 30, 15, there's 25. Yeah, this one here is a weird jump, so that's the one that screws up the data. And then it's back on track here. So it's going 10, 15. That should really be 20, 25, 30. So if you were to massage this data and look at sort of a better idea of what's going on, it would look like that. And then if you looked at the next differences, it becomes negative 5, negative 5, negative 5, negative 5, negative 5. What is that? Well, they're all the same. Therefore, we're dealing with a downward facing parabola as opposed to a growth curve. Otherwise, you'd see multipliers the whole time. And yeah, I'm fudging it. And yeah, it's not right when I fudge it like that. But it's quite clear that the numbers kind of do some weird deviations, whereas the consistent pattern is we're going down by 5 each unit of time. Given that, I know that I'm dealing with a parabola, and if I wanted to have it figured, I'd do the little sigma choice, and I would do A, and I would do Y1 here to let it know I'm dealing with the chart up above of A, X1 to the power of 2, and then it's plus 400. Didn't quite get it, did it? Plus 400. Oh, yeah, 0, it's 400. X1 squared for sure. And A. It didn't quite fit it. It's, you know what it's doing? It's using these last two dots, and it's ignoring those first three dots. So it's really trying to fit it with a line that best fits. And it's saying A is minus 3. I think it's probably more likely minus 4 x squared plus 400. Let's see if I get one. Mine's about the same. I think mine's a little bit better fitting. That's minus 4.2. How about 4.5? How about 5? How about 6? 6 is off. 5 is closer, but I would say 4.5 is probably the best one. So let's turn this off to see. I mean, yes, no, it depends which data points are more accurate. I think that one's pretty good. And then what's the last question it's asking? Instant rate of change is exactly 4. Okay. We're going to do m is equal to open brackets f of 4.0001 minus f of 4, all divided by 0.00001. Negative 36. So that's what my calculator is changing at, negative 36 degrees per minute. I think it was per minute, right? And then if I did the actual 4 minutes, I would have to take it on this side and then on this side and take an average. And then maybe take it from 3 to 5 and then average those all together. Do I want to do it? I mean, I can. I guess I'm supposed to do it. Okay, let's do it with the actual data. What's the rate of change here? It's just 1. How much did it change? 20. So how fast is it changing? 20. What's the rate of change here? It changed in temperature 25 in 1. So I got 20 and 25. How much did it change from 3 to 5? It changed 45 in 2 seconds, which is 22.5. If I add those all together, I get 25 plus 24 plus 22.5. I get 49, 51, 71.5 divided by 3. 71.5 divided by 3. I'm getting a decrease of 23.8. What did my thing say? Ooh, shows you that this is not as accurate as the one they gave us. Let's try 3.6 as the one they gave us. And they're saying negative 28. So why the discrepancy? It's quite obvious. The graph doesn't fall perfectly on all these points. I would suggest that the actual data is more accurate than the interpretation of the graph. Now, if you had a perfect data of going down 10 each time, it would be able to figure out the graph perfectly. Oh, and I think I put this one in wrong. That didn't help me, did it? No, oh, wow. What's going on here? 305. Oh, did I get it right? Yeah. And it's pretty obvious that it can't come up with a graph from so many limited points. I think I would have stretched it more, made it 4.6. That's probably more accurate to what's going on. By the way, did I get the right average? I had a difference of 25. Oh, that was a difference of 20, a difference of 25. Ah, there we go. I have a difference of 20 plus a difference of 25 plus a difference of 22.5, all divided by 3. Yeah, so this is showing a much more consistent decrease of 22 degrees, and this is showing 36, so it's way off. And the point we're interested in is around here. I don't know if it's that accurate, to be honest with you. I think the actual data is more accurate. Okay, sorry, I'm rambling. Just be sure to play at 2 times the speed. In the table like the one below, nah, I'm not doing that. Concentric circles from a stone is dropped into a pool. What is the average rate of change of the area circles? From 0 to 100, and how fast the area changing at exactly 120. Interesting. So the interesting thing about circles is their area is based on the square of the radius, pi r squared. So if you look at it in a formula, and this is probably your best bet, is you should look at it like this. F of x, or the radius based on time, is going to be pi r squared. Area based on radius is going to be pi r squared, which means, and I'm only interested in where r is bigger or equal to 0, which means you can see the areas of those circles are getting bigger and bigger and bigger. So if I look at area when the radius was 10, or 100, and I look at the area when the time was 0, it was 0, you can see that the rate of change is going to be 31,415.9265 divided by 100. Rate of change is 314. What does that look like? The rate of change is pi times 100, right? Why is it pi times 100? Because we took the area of 100. That's interesting. What about the rate of change when it just asks us to calculate the instantaneous rate of change when the radius is 120? Okay, well for that I'm going to skip these two, and I'm going to call my rate of change m, and I'm going to call it a of r plus h, which is 120 plus h, minus my a of 120 divided by h. Now I need to know what my h is. H is equal to 0.00001. My rate of change at 120 is 753. And if we want to put it into 0001 instead, just to make sure we got it right, 0001 divided by 0.0001. Rate of change is 753. So you can see the 314 appeared because we happen to be using an area of 100 at that time. And it multiplied pi, made pi appear. A crystal in the shape of a cube is growing in the laboratory. Estimate the rate of change surface area is changing with respect to the side length when the side length of the crystal is 3. So how fast is the area changing at 3? Well, that's a cubic. So area is equal to x cubed. And it wants to know how fast is this changing? How fast is the area changing? And that's ax. And x is the side. How fast is the area changing at 3? Well, that's area of 3.001 minus the area of 3, all divided by 0.001. And it's changing at 27, which makes sense, because 3 cubed is, well, no, that doesn't actually make sense. Yeah, well, I guess that does make sense. It's changing at the rate of its volume per meter at that time, which is 27. If I put that in terms of h plus h all over h, and then I make my h whatever I want. Let's take h from 0.0001 all the way up to 5. Okay, you can see I'm going to get more and more accurate as I get close. Even then I have to take smaller steps to 27. And actually, if you put it between that and 0.001 and hit it, you get a better idea. And even 0.1. Let's make our h1 go all the way up to 0.1 instead of 1 and hit play. So you can see as I get up to h is 0.1, I'm not as accurate to the 27. So the answer to that is 27. Spherical balloon, estimate the rate of change with the surface area. So you got to look up the surface area of a balloon for that. This I'm going to save till next time because I got to go. Long session. Play at double speed.